Hello everyone, and welcome to your linear algebra review on non-examples of subspaces. My name is Jason, and I work for the ASU Tutoring Centers. Now, in the previous video, we talked about examples of subspaces, right? There's sort of four general rules that you need in order to be a subspace. The first of all, you need to be a subset. So in this particular case, right, our vector space is R3, and this set that we're looking at, W, takes vectors that are three-dimensional. So all of its vectors come from R3, so it is a subset. Okay, so that's a check, that's fine. What else do we need? We need there to be, we need our subspace to be non-empty. And typically the easiest way to show that is to show that the zero vector is in it. In fact, the zero vector has to be in your subspace. So if we were to check real quick, is the zero vector in here? Well, what does it mean to be in W? It means that X, Y, and Z all have to be greater than or equal to 0. That's the rule. In order to be in W, all three components have to be non-negative. So in particular, 0, 0, 0 satisfies that rule, right? 0 is greater than or equal to 0, 0 is greater than or equal to 0, and 0 is greater than or equal to 0. So all three components are greater than or equal to 0, so it is in W. So W is a subset, and it also has the 0 element, so those rules are satisfied. So that means since this is a non-example, it either fails at vector addition or it fails at scalar multiplication. Let's look at scalar multiplication. So again, if we're trying to show that this is a non-example, all we have to do is find a counterexample. We have to find an example of a scalar and an example of a vector in W, such that when we multiply them together, we get a vector that's not in W. And a perfect example of that is let alpha equal -1, let that be my scalar, and consider the vector 1, 2, 3 in W. Doesn't even matter. First of all, 1, 2, 3 is in W, right? Because all three components are non-negative. They're all greater than or equal to 0. So this is in fact in W. But let's see what happens when I do my scalar multiplication, when I take -1 and I multiply by 1, 2, 3. I get -1, -2, -3. Is this in W? Well, no, this is not in W. Why? Because in order to be in W, all three elements have to be greater than or equal to 0. And in fact, in this case, none of the elements are greater than or equal to 0. They're all negative. So when I did my scalar multiplication, I took an arbitrary, or not an arbitrary, I took a specific scalar, a specific vector. When I multiplied them, I got something that was not in W. So I found what we call a counterexample. I found something that proves that this is not closed under scalar multiplication. Okay, as long as you can find just a single example that fails, then you know for a fact that it's failed entirely. It is not closed under scalar addition. Because to be closed under scalar addition has to work for every single scalar and every single vector. So if it fails even one of them, it is not closed under scalar addition. Therefore, W is not a subspace of R3. So typically, it's easier to show things are not subspaces than it is to show that they are, because to show they are subspaces, you have to take two arbitrary elements, do some funky stuff with them, and show that you're still in W. But to show that they're not a subspace, you just have to find a single counterexample. That's all it takes. Either a counterexample showing that it's not closed under scalar multiplication, or a counterexample showing it's not closed under addition. Okay. Wonderful. Thank you all for joining me. As I mentioned at the beginning, I work for the ASU Tutoring Centers. If you want more information on the free tutoring services we offer on all 4 major ASU campuses and online, please check out tutoring.asu.edu. If you want more videos like this that go over specific concepts from your course, or you want to see what upcoming review sessions we have for the exams in your course, please go ahead and check out this link below. Thank you all again, and have a fantastic, fantastic day.